So today we'll take another shot at review of acids, bases, and pH. This review is going to be based on the review document. And as a matter of fact, I don't have that pulled up yet. So let me, there, how about that? All right, so as customary, I picked out a few problems that I think would be useful, and I marked them off on my hard copy. So we'll just get started. Unless you have any comments or questions before we get started. Okay, I'll take that as a no, and we'll go to number 3. The concept of conjugate acids and bases. So for number 3, we've got these selections, A through D, actually. Right. First one is this. Next one, HF and NH4. And then, of course, this one is all. Okay, the object of the question is, which of the following is the strongest conjugate acid? Okay, so a conjugate acid must be formed from a base, correct? A conjugate acid can donate a proton. A conjugate base from which it was derived can accept a proton. So if we look at it in those terms and treat each one of these as an acid, which is how they're defined, which one is the strongest conjugate acid, then what would happen to this acid? It would have to lose a proton. And what's left over? The OCl there. Right? So this is the conjugate base of that acid. Conversely, this is the conjugate acid of that base. Okay, this one would be Cn minus, this one would be F minus, and this one would be NH3. Okay, what we have to do here is decide for it to be the strongest acid, it would have to be the most dissociated in the process. So which one is more likely to lose a proton than any of the others? Personally, I would think that if we have any acid in there that is derived from a halogen, like fluorine, chlorine, bromine, iodine, then that would be stronger than any of the others. Simply because the halogens are the most electronegative in their periods. If you go from left to right, the most electronegative is on the far right. And electronegativity means they're pulling electrons to themselves. And if they pull electrons hard enough, it makes it really easy for that positive to leave each one of those protons. So my guess would be this one is the strongest acid of all of them. Now, if you have more than one halogen, so if we have HF compared to hydrochloric acid, hydrobromic acid, hydroiodic acid. The strength of the acids increase from this going up the group like that until you get to this one. Hydrochloric is the strongest. HF becomes a little weaker than this one, but it's still pretty strong. And by comparison to these others, it's stronger than the rest. So that answers the question there. That one is the strongest. Didn't want to erase very well today. Okay, so that was number 3. How about number 4? Calculate the hydrogen ion concentration in a solution that has a pH of 8.82. All right, so if the pH is 8.82, right, where did that come from? That came from this expression. And the question asks, what is that concentration? So how do we do that? Well, first thing you have to do before you can resolve this log function, you've got to move that negative. You can't leave the negative there and proceed with the anti-log is where we're headed. So you have to move this negative over here. Negative 8.82 equals the log of this one. And then we look at the way logs are defined. This is the base 10. What that means is base 10 to that power equals that number. So when we say anti-log of negative 8.82, we actually mean 10 to the minus 8.82 power. And that's equal to the hydrogen ion concentration. So all we have to do is find that key, 10 to the x power, find that key on your calculator, and then put in 8.82 negative. And then we get, well, let's see, we have 2 decimal places here, which means we can have 2 significant figures, correct? 2 significant figures in our answer. 1.5 times 10 to the minus 9. Molar. All right, and that appears to be A. All right, so let's look at number 5. I've got that one checked also. Okay, so what are we given? A solution is prepared by dissolving 111.9 grams of HCl gas in enough water to make 160.0 liters of solution. So the mass of HCl is 111.9 grams of HCl. Okay? And the final volume is 160 liters. Okay, so how are we going to find the pH out of that? First, you have to recognize that hydrochloric acid is a strong acid. If you've got that much hydrochloric acid, all of it goes into solution. So in order to calculate the pH, we need to know the molar concentration of hydrogen ions. So that means we got to change this to moles. You can't work with grams. So we need the molar mass of hydrogen chloride. Right? Grams on top, grams on the bottom, they cancel. So now we just need to add it up, and I already know what it is. It's 1.01 for hydrogen and 35.45 for chlorine, 3646. Okay, so we'll just divide that into 111.9 is 3.0, 4 places, 3.069. Okay. Now, since that's a strong acid, how many moles of hydrogen do you have? The protons, hydrogen H pluses. You got the same number of moles, because for every 1 mole of HCl, you get 1 mole of hydrogen ions. So to calculate the concentration of hydrogen ions, we have moles divided by volume. Like that. Divided by 160.0 liters. And we can use that volume because it's already in liters. It has to be in liters to give you molar concentration. So we just need to divide this value by 160. And let's see, we got 4 significant figures. 1.918. Times 10 to the minus 2 molar hydrogen ion concentration. Okay, now we can calculate the pH. Right. All we need is the negative log of 1.918 times 10 to the minus 2 . So I'll take the log of that and change the sign. So we've got 4 significant figures here. So we can have 4 decimal places in our pH, which would be 1.7171. Now the answer is probably rounded off. So let's see if there's one that's close to that. It looks like D is the best fit. 1.72. They rounded it off. Yeah. 4 significant figures means 4 decimal places in our pH value. So that takes care of number 5. How about number 6? There, I moved too far. All right. Let's make some room. Okay, number 6. A solution has hydroxyl concentration of 5 times 10 to the minus 4 molar. What's the pH? Okay, so we're given hydroxyl ion concentration equals 5.0 times 10 to the minus 4, wasn't it? Yeah, minus 4 molar. And the question is, what's the pH? Okay, you can approach this a couple of different ways. You can either use the equilibrium expression for water and determine hydrogen ion concentrations, and then calculate the pH. So let's do it that way first. So what's that expression? Kw equals 1 times 10 to the minus 14, which is equal to what? Hydrogen ions times hydroxyls. Okay? That being the case, we know what hydroxyls are. We just need to solve for protons. Right? So the hydrogen ion concentration is going to be what? 1 times 10 to the minus 14 divided by 5 times 10 to the minus 4. Okay? You can use your calculator if you want. 1 divided by 5 is what? 1/5, which is 0.2. And then this is minus 14 plus 4. This minus 4 goes into the numerator, changes the sign. So this is times 10 to the minus 10, right? Which is equal to 2 times 10 to the minus 11 molar hydrogen ion concentration. Hello? Then want to talk to me. Okay, now we have this value, we can calculate pH. So we just need the negative log of 2 times 10 to the minus 11 molar. Okay, so I use my calculator for that one. Take the log of that and then change the sign. So we've got two significant figures here. I can have two decimal places. 1.07. Hold on a second. Oh, that's 10.7. Excuse me. I wasn't watching my exponent. 10.7. Which makes more sense. This concentration is much greater than 10 to the minus 7, isn't it? Which means it's basic. And if it's basic, then the pH should be greater than 7. Right? 1.07 is not. That's what triggered it for me. I knew it had to be basic. So I didn't write the wrong number down. I checked myself and found that my reading was wrong. It's 10.7 pH. Okay. So that would be B. That's one way to solve the problem. We know another way. What's the other way? Find the pOH. Okay. So the pOH is what? Well, we need our calculator for that one. pOH is 3.3 3.30. Okay, 3.30, that's correct. And then we also know the relationship is pH plus POH equals 14. So if we know this one, right, then pH is equal to 14 minus 3.30, which is 10.7. So we get the same answer either way. I like this way better. That was number 6. Okay, go. Check that one off, and let's see what's next. Okay, number 7. Okay. As water is heated, its hydrogen ion concentration increases. This means what? You have several selections here. So let's map it out. Water temperature is increasing. Hydrogen ion increasing. Okay. Now, let's look at this first before we look at those answers. Let's be sure we understand what's happening here, right? This is just water. We're not concerned with anything else but water. So what do we know about water? In the simplified version, water dissociates into protons and hydroxyls, correct? At 25 degrees C, the concentration over here is 10 to the minus 7. What's the concentration of hydroxyl? 10 to the minus 7 molar. How do we know that? That's because there's only water in here. Pardon me for a second. Hello? Yes, ma'am. Tomorrow at 11. Yes, ma'am. You're on the schedule. You too. I always answer doctors' calls. Okay. So we know because the source of each one of these is the same. It came from that water molecule. So if you get one of these, you get the same number of these. All right? So if the water temperature increases and hydrogen ion concentration increases, what does that mean? That means this is increasing, but that also means that this one is increasing at exactly the same rate. So if you have a concentration here that jumps up, it's going to be exactly the same as this one. Which means what? Well, if hydrogen ion concentration and hydroxyl ion concentration are equal, what does that mean for the pH of the solution? It's neutral, right? It's still neutral. Even though this increases, so does that. which makes it neutral. All right. So what are our choices? Well, A says water is still neutral. That's true. A is true. How about B? Hydrogen ion greater than hydroxyl? No. Hydroxyl greater than hydrogen ion? No. OH minus also increases. That's true. D is true. Right? So that means E is also true, because it says A and D are both true. So that's why the answer is E. There's nothing magical about this. We're not making an acid by heating the solution. We're just changing the equilibrium. And since we're changing the temperature, I don't know if we covered that in our equilibrium discussion, but I'll cover it now. When you change the temperature of a system like this, you also change the equilibrium constant. The equilibrium constant is dependent upon the temperature. But to answer the question, the source of these two is the same source, 1-to-1, so they're always the same concentration no matter what the temperature. If there's nothing else in the solution, if it's just solvent, nothing else in there, then that's the way it is. Well, actually, if you put a solute in there, this is still going to be active. It's going to be the same equilibrium whether you put an acid or a base in there. You'll still have this, and you'll have your new equilibrium constant at a given temperature. All right, that was 7. Let's see here. Check that one off. I don't have 8 checked, but let me see. Let's do 8 also. Okay, so the question references that balanced equation, HSO3 minus plus cyanide ion yields what? HCN plus SO3 2 minus. Okay, what they want us to do is identify the Bronsted acid and the Bronsted base, right? So there's going to be 4 possible answers, 1 for each of the reactants and products. So we have to decide which one's acid, which one's base. So let's start on the reactant side. Hello? Where is this proton going, right? There's only 1 proton over here, so that we have to focus on that one. So where does this proton go? It goes there. That means this is the acid and this is the base. All right. So on the other side, where's the conjugate base for this acid? Well, it's that part, right? We lost 1 proton, so we have this left over with a change in the charge, of course. So that means this is the conjugate base of that acid. This must be the conjugate acid of that base. So the answer would be ABAB. This one right here. Okay? Now, I'll get back to the ones I checked off. Let's see, here we go. Number 9. All right. Which of the following is a conjugate acid-base pair? All right, we know what the rules are. Right. Hello? No answer. So we have these pairs to choose from. And E. All right, the first one we have is HPO4, HPO4 2 minus, and PO4 3 minus. So what do you need to have an acid-base pair, a conjugate acid-base pair? Well, you need, of course, to have an acid, right? You need at least one proton. So there's a proton right there. So if that's the acid, what happens to it to make the base? You lose one proton only. And what's left over? What's left over is that part right there with a charge change, right? Because if this proton leaves as a positive, it left an electron behind, which means now this is 2 minus changed to 3 minus. PO4 3 minus. That is an acid-base pair. That's true. How about this one? HNO3 minus, HNO3 minus, and H2NO3, H2NO3. Right? You got protons. If this is an acid and you lose that proton, this is NO3 2 minus. If you take this one, well, that's not the base of this acid. Acid-base pair. So that can't be it. Besides, that species doesn't exist. It can't exist. HNO3, yeah, that's nitric acid. But that one, no, can't exist. But if this is an acid, then that's not the base. How about HNH4? HNH4 makes NH4 there. If you lose this proton, then it's NH4 minus. That's NH4 plus. Or even if you went backwards, NH4 plus as an acid would give you NH3 with no charge, right? So that one can't be right either. How about D? H2F and HF minus, right? If we did lose a proton here, that would be HF minus. But these species cannot exist. HF never has a charge. HF is an acid, hydrofluoric acid. So it would produce F minus as its conjugate base. So I don't know why they put these weird ones in here, because they don't make any sense. H2CN, H2CN, CN minus. All right. The only way that this could be the base of that acid is if it were HCN and not this one. But that's not the problem. It just doesn't work. The only valid one in this group is A, right there. Conjugate acid-base pair. Okay, how about 10? Choose the case that is not a Bronsted conjugate acid-base pair. All right. So that means since A through E, we have pairs in every one of them, all we have to do is go down until we find the one, right? And then we can stop, because there's only one answer. All right. So let's do A is, we just did this one, right? That's an acid-base pair. How about this one? CH3 NH3 plus. CH3 NH3 plus. So what would you have to do here? Lose a proton, right? Lose a positive hydrogen. That leaves CH3 NH2 with no charge. Is that it? Yep, that one's good. How about C? HCO2H. HCO2H. So, which one of these are we going to lose? We'll normally put the H first. That's the acid hydrogen. But this one could be like that. HCO2H. That's formic acid. And in this case, that one is the one that leaves. So we would need HCO2 minus. Is that what we got? Nope. Actually, look, we're missing an oxygen. There's one there, and there are two here. You can't lose an oxygen and claim it's an acid. So C is our answer. That one is the one that's wrong. We can look at the rest of them. Boric acid, we've lost one proton right here, right? Make it a negative. That's true. This one, which is what? Chlorous acid. ClO2 is chlorite, so this would be chlorous acid. And then we lose a proton, and ClO2 minus is correct. Right? So C is the only one that's wrong in this whole bunch. All right. I've got 11 checked off. Let's see what 11 has to offer. Okay, we've done one like this before. On the first page, calculate the hydrogen ion concentration for a solution that has a pH of 9.16. So if 9.16 equals negative log of hydrogen ion concentration, we just need 10 to the minus 9.16. And let's see, there are 2 decimal places, so we can have 2 significant figures. 6.9 times 10 to the minus 10. Molar. And there it is, right there. All right, that was 11. Let's skip down to 15. I'm going to look at them as I go, see if there's anything. We've done one like that before. Let's do 14. I think 14 has value. All right, a solution with a pH of 3 is how many times as acidic as a solution with a pH of 5? So we have 2 solutions, pH 3 and pH 5. And the question is, how many times as acidic? So what does that mean? What that means is, what's the ratio of hydrogen ion concentrations? Right? What's the hydrogen ion concentration here? Well, pH 3 is easy. That's the third power. That's the negative third power of so this one would be 10 to the minus 3 molar. And this will be 10 to the minus 5 molar, correct? Right. So, if that's true, is this a valid question? First of all, is pH of 3 greater than pH of 5 in hydrogen ion concentration? Well, yeah, minus 3 is bigger than minus 5 powers of 10. So now we can do the ratio. So how much bigger is this one than that one? What's the ratio? Well, the ratio is 10 to the minus 3 divided by 10 to the minus 5. Right? So 10 to the minus 5, if you bring that into the numerator, it becomes 10 to the minus 3 plus 5, correct? So that is 10 squared. It's 100 times more acidic. Now, why is that? That's because pH is on a logarithmic scale, base 10. So whenever you change the pH by 1 unit, you've changed the hydrogen ion concentration by a power of 10. If you're going this direction toward larger, then it's 10, 100, 1,000 times. If you go in the other direction, it's a 10th, 100th, 1,000th. Okay? So the point of this, the moral of this story is pH is a logarithmic scale. And this is an arithmetic scale, which means it's the ratio is unitary. Right? 100 times equals 2 pH unit change. Let's see, I didn't say what that was. There it is, 100 times. E. Okay. Let's see if I'm still centered. Yep. Let's see. Oh, now we can go to 15. I had a detour on the 14th. Okay. Calculate the pH of an acid solution containing 0.044 molar HNO3. That should be fairly simple. 15. We're given, molar concentration of hydrogen ion is equal to 0.044 molar HNO3, which is actually true. If this is the concentration of the acid, then that's also the concentration of the hydrogen ions, because you only have 1 proton for each mole of HNO3, which means this molar is the same as that molar. What if this were H2SO4? That's not the problem, but I'm just curious. H2SO4, if it were this concentration, what would be the hydrogen ion concentration? Well, it would be twice, right? So 0.088 mole. Okay. So now all we have to do is calculate the pH. We take the negative log of this number. Let's see. 2 significant figures, right? These 2 zeros don't count. They're just placeholders. So 2 significant figures means 2 decimal places. 1.36. And that should be A, right there. Let's see, I got 16 checked off also. We're doing a lot of repetition here, aren't we? What's the pH of a 4.9 molar solution? Right. Again, if that's 4.9 molar in perchloric acid, then it's also 4.9 molar hydrogen ions. So we just need the negative log of 4.9 molar. Now my guess is that high concentration is going to give you a negative pH. Let's see if I'm right. 4.9, and we'll take the log of it and then change the sign. Yep, negative 0.69. Yep, negative 0.69 pH. Now, is that valid? Can we do that? Yeah, we can do that. This just is a mathematical expression, log of a number, right? You can do that for any rational number. You can take the log of it. I don't know what to do with irrational numbers. I've been out of math too long. It may be impossible. That was 16. Oh, I didn't mark off the answer. 16. There it is right there. All right. 17. Yep. I got 17 marked. What's the pH of a, 0.25 molar acid, nitric acid solution? Actually, repetition is good. It's almost like muscle memory. If you do it enough, you can do it in your sleep. 0.25 molar nitric. 0.25 molar. Can I do that? Yeah. 0.25 molar nitric is the same as 0.25 molar hydrogen ions because it's a strong acid. And there's only one proton per molecule. So let's see, 0.25 molar. Take the log of it and change the sign. So I get 0.6, 0.60. 0.60. Right, 2 decimal places, 2 significant figures. So that looks like C is the answer. How about 18? I think we've done one of these before too. So which way are we going to answer this one? 18. pH of 3.16. pH equals 3.16. And the question is, what's the pOH? pOH. Oh, that one's easy, right? We know what the relationship is. If you add those two together, you get 14. So if you subtract this one from that one, then you get 4, 8, 10. 10.84. 1. Yep. pH. 10.84. So what does that say about the solution? Oh, I'm sorry. No, that's right. This is pH. No, pOH. And this is pOH. There we go. Now it's right. Because this is the pH. So the POH is subtracted from 14, gives you 10.84. Right there. Okay. Let's see. Let's go down to 20 if 19 looks, yeah, we don't need to do 19. Which of the following is true for a buffered solution? All right, go back to your definition. What is a buffered solution? A buffered solution resists change in pH. Okay, let's see if any of these match. It says all of these. Okay, so it could be all of them. The solution will not change its pH very much, even if a strong base is added. A is true. The solution resists any change in hydrogen ion concentration. B is true. C, any hydrogen ions added will react with a conjugate base of a weak acid already in solution. Is that true? Well, what's in solution? You got a combination of a weak acid and its conjugate base, correct? So you have the acid, and it's going to react with water, of course, and it's going to produce hydronium plus. From the acid, we make a conjugate base. So when you add hydrogen ions, where are they going to go? They're not going to go over here. They're going to go over here. Right? And that makes more of this. Okay? So, is that true? Any hydrogen ions will react with the conjugate base of a weak acid. That is true. How about D? The solution will not change its pH very much, even if a concentrated acid is added. That's the same way of saying A. Yeah, so D is also true. It's just worded differently. So the answer is E. All of these are true. Okay, that was 20. Let's see, let me scroll down. I'm headed for 24, but let me see if any of these others would be valuable. Those are repetition. 24. Oops, excuse me. Okay, this is also repetition, but I'm going to do it anyway. A solution, we're given a solution that has an OH concentration equal to 3 times 10 to the minus 7. There we go. Question is, what's the hydrogen ion concentration? Okay. Remember from earlier problem, this one times that one is 1 times 10 to the minus 14. Okay. Because that is equal to kW at 25 degrees Celsius. So if we plug this one in here, we can solve for that unknown. It's just a math problem. That means this value is equal to this one divided by that value. Okay? You can use your calculator if you want to, but sometimes I like to do it in my head if I can. So 1/3 is 0.3, let's see, two significant figures. 3 times 10 plus 7 would be 10 to the minus 7, which is equal to 3.3 times 10 to the minus 8 molar. That's your hydrogen ion concentration. It looks like they rounded it off. No, they didn't. There it is right there. I was looking at A. That's the wrong answer. Okay. So there you go. That's number 24 is D. All right, let's see what's next. Okay, I'm headed for 27. Let's see if I get sidetracked on the way. Nope, 27 is good. There it is. What does 27 say? A weak acid, HOCl. What is HOCl? OCl is hypochlorite. So that would be hypochlorous acid. Is in a solution with dissolved sodium hypochlorite. Right? You know what sodium hypochlorite is. Well, if it's 5 or 6%, I've seen 1.5% on the shelves. Concentration in aqueous solution, that's bleach. So you can have a weak bleach, you can have a strong bleach. All right, so if this is in solution with sodium hypochlorite, then if hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? Right? So the equilibrium reaction that establishes, this is a buffer, is this one, right? And now, do we have those in solution? Well, yeah. The first part of the statement says the weak acid is in solution with dissolved sodium hypochlorite. So what happens when you put sodium hypochlorite in solution? It breaks up completely and makes sodium ions and hypochlorite ions right there. This one is a spectator. You could do the same thing with potassium hypochlorite or lithium hypochlorite. It'd be more expensive, but you could still do it. The hypochlorite ion is the key. That is the conjugate base of a weak acid, which makes it a very strong base. All right, now if we're going to add hydrochloric acid to the solution, what does it do? Well, it makes hydrogen ions plus chloride ions. All right. What does that matter? The chloride doesn't react with anything up here, right? It's not going to react with hydrogen because it just gave up hydrogen. It's not going to react with another anion. And it's not going to react with this one because this one is a weaker acid than this one is a base. It's not strong enough to strip that proton from that weak acid because that acid is, it's weak because it's holding onto that proton, right? So this is also a spectator along with sodium. So this is the only thing there is to react, and it's going to react with that one to make, actually, it's going to make this one. Okay, so let's see which statement is correct. Which ion will react with extra hydrogen ions to keep the pH from changing? This one right here. Right? We just showed that right there. That was 27. Okay. Get back on track here. 27 is done. Okay, I'm headed for 30. Let's see. How about 28? Let's do 28. Okay. Of these following statements, which one is true for a strong base solution with a concentration greater than 1 molar? So the concentration of our strong base is greater than 1. All right? So if it's a strong base, what does that mean? Well, that means the hydroxyl concentrations are also greater than 1. You know, even if there are 2 hydroxyls here, we drew it with 1 hydroxyl. But if there were 2, it's definitely greater than 1. If this is greater than 1, 1's greater than 1, but 2 is even greater than 1. So what can we say about these statements? A, is this true? pH is greater than pOH. Well, ask yourself, is this solution basic or acidic? Right? You've added 1 molar, greater than 1 molar hydroxyls. What does that tell you about that solution? It's definitely basic, right? So if it's basic, that means pH has to be greater than pOH, right? Anything greater than 7 is basic. So the pH will be much, much greater than pOH. That one is true. How about B? pOH is greater than pH? Well, you can't be both right. We know this one's true, so that one's false. How about C? pH is less than 14. pH is less than 14. Well, let's do the calculation. What would the pH be if the molar concentration of OH were 1? Let's just do that. So let's say 14, and take the log and change the sign. That's negative 1.1 pOH. Negative 1.1 pOH. So what is the pH? Well, you subtract that from 14, right? So 14 minus a minus 1.1 is equal to 15.1. Right? pH is not less than 14. It's actually greater than 14. Right? So this one's false also. pH less than 0? No, the pH is 15.1. pH can't be less than 0. pH less than 0? That's false. So, if all of them are false except for A, then E can't be true either, because it says 2 of these are true. Only one of them is true. That's this one right there. Okay, that was 28. Let's see, 29. No, we've done one like that several times, as a matter of fact. How about 30? A solution with a pH of 2 is how many times more acidic as a pH of 6? Okay, let's see if we remember what we learned in that previous problem. If the pH is 2, compared to a solution of pH 6, how many times more acidic is the pH 2 than the 6? First of all, is that true? This is more acidic than that. Yes. pH 2 is smaller than 6. So this one's more acidic. But how many times? Well, here's the easy way to do it. What's the difference between 6 and 2? It's 4, right? 6 minus 2 equals 4. So what does that 4 mean? That 4 is the power of 10, which is 10,000 times. 10,000 times more acidic. We could have gone through that whole calculation again, but this is simpler. So that means D is the answer, 10,000 times. What would it take to be 100,000 times? Right? What's 100,000? 100,000 is 10 to the 5th, isn't it? So if it was 100,000 times, what would be this one? Well, that would have to be a difference of 5. So you could get that by either saying this is 7 against 2, or you could say this is 6 against 1. Same answer. Now, those are just 2 examples. I mean, you can think of a dozen different answers that will give you the same difference of 5, power of 10. All right, let's see. Okay, I'm headed for 32. Yeah, we don't need to do 31. A buffered solution contains HNO2. It also contains, aha. Now we'll see if you're paying attention during buffer discussions. Let's see, where am I? 32? 32. All right, our buffer contains what? If it contains HNO2, right, that satisfies one condition of a buffer. If it is a weak acid, is HNO2 a weak acid? Yes. HNO3, nitric acid, is strong acid. But HNO2, nitrous acid, is a weak acid. So what else needs to be in that solution to make a buffer? The conjugate base. Right? Needs to have that one. Well, how are you going to get it in there? You can't add it as acid. If you add it as acid, it just gets more acidic. Right? So you have to add this as the salt. So some cation attached to that nitrite anion will put it in solution, and then the cation will be in a spectator, excuse me. So which one has NO2 in it up here? It looks like the only one with NO2 is this one right here, KNO2. Right? So it just needs to be soluble, right? Because you have to put that in solution. That has to be aqueous. Just like this one. So is KNO2 soluble? Yeah, it's very soluble. And it makes potassium ions and nitrite ions. So there you go. And in fact, the best ratio of this one to that one, the best molar ratio is 1 to 1. equal numbers of this one and that one in solution. We didn't have time for that discussion in this class. It's a little deeper than the class calls for. But if you're interested, equal amounts is the best buffer for the acid, the weak acid, and the conjugate base. All right, that was 32. 32. I got 33 checked off. Let me see. Consider this reaction. HC2H3O2. What is that? That is acetic acid in solution. Of course, well, yeah, it's acetic acid. Let's just leave it at that. So if we react acetic acid with water, what do you get? Well, the acid transfers a proton to water, makes a hydronium ion, and leaves an acetate ion behind. So which one is the conjugate acid? Well, if this is the acid, what is this? It receives the proton, so it's the base. So if water's the base, what's the acid? Well, add a proton to it, and that makes it an acid. H, the hydronium ion, is the conjugate acid. Right here. There. That's the conjugate acid. I didn't even have to put that one on the board. Let's see, 35. Which of the following is not a conjugate acid-base pair? All right, so we could probably do this one without putting it on the board too. Is this a conjugate acid-base pair? Remember, two conditions. Well, I will put it up here after all. Two conditions. One, only one proton transfer. All right. So let's see if there are any like that. This one transferred 2 protons to get that. This one transferred 1. This one transferred 1. This one transferred 1. Leaves us with that one. This one transferred 1. Okay, so that condition is met. Except for A. A's wrong. Right? So, I mean, if you're in a hurry on a test, that's your answer. Because it didn't meet the first condition. Second condition is the anion formula is preserved. What does that mean? That means if the conjugate base has lost a proton, that means that whatever is left over has to be present on both sides. There and there. It's present, but it got there by losing 2 protons. Okay. This one is true here. There you go right there, and there's the anion. There you go, and there you go. Right. That one's true. All right. This one includes one of those protons. You only lose one, so you have to have the proton here, and there's your counter ion. And then bromine is there and there. So all of those match both conditions, first and second conditions. All right, 35. Let's see. We don't need to do 36. We've already done that one several times. 37, is that on my list? Yeah, 37. Which of the following is the strongest conjugate base? So A, B, C, D, O, and E, all the same. That's not likely, but we'll put it there anyway. So we're comparing these And we want the strongest base out of this bunch. OCl minus, NH3, and F minus. Okay. So which would be the strongest base? It would be the one that's derived from the weakest acid. All right. So what would be the acid that would give you that conjugate base? Well, we have this one. Oops. There. We have this one. We have this one. And we have this one. Okay. So this one is probably the strongest acid of that bunch. So this is going to be the weakest base, right? We can throw it out right now. How about the others? Well, let's see, strongest conjugate base. That's kind of hard to tell, isn't it? Without the numbers. I mean, if we had the equilibrium constants for each one, we could tell. Well, let's see. What about these two? Oops. Right. Hypochlorous acid here is in sequence with perchloric acid, chlorous acid, then hypochlorous acid. So the its family has a good strength. And this one would be a weaker acid than that one, so it'd be a stronger base. So this was actually a stronger base than that one. Now we have to decide which one of these is the stronger base. Okay. Well, strongest conjugate base. The stronger base is the one that latches on to a proton. And I think there's an error in this one. How do I know that? No, there's not an error. Excuse me. There's not an error. And you wouldn't know this, but I'm going to tell you now. I've done the calculations. And if you have these two in solution, if you put ammonia in solution, that's what this is, ammonia, you're going to have greater than 99% of it in this form. So this is going to be let's see, if this is the base, it would want to be over here, right? So there is a problem. That's a weaker base than this one is, right? So I would say A is the answer, and this is an error right here. That should be A. Now, the only way to be absolutely sure is to look at their equilibrium constants. Compare them. But for now, I'm going to say A is the answer to that one. It's the strongest conjugate base. It probably would have been better to say which one's the weakest conjugate base. That would be, hands down, no problem, fluoride. That's the weakest base. Because it comes from not a strong acid, but pretty close to a strong acid. So I'm going to make myself a note here on 37. Check that one out. And then what I'll do is, if it's different than what I said here, if A is not the answer, if I've got reason to go back to C, then I will put that as a subtitle in the video. So if you watch the video, when you get to this point, you'll see a subtitle explanation there. Otherwise, A should be the answer. All right. So how about 38? Calculate the OH in solution that has a pH. We've done that so many times. You just calculate the pH, subtract it from 14. Well, actually, no. Yeah, you could. Subtract it from 14 gives you POH. Then take the antilog of the negative to get the OH concentration. That's fairly simple. How about 39? Calculate the hydrogen ion concentration in solution that has a pH of 5.54. That's even simpler. Take the antilog of negative 5.54, or 10 to the minus 5.54 is the answer. 40. Okay, we'll do 40. We can't skip them all. So we'll give this one repetition. So you put solid calcium hydroxide in water until the pH is 10.39. Calcium hydroxide has limited solubility. So you're going to have a lot of solid calcium hydroxide on the bottom of your beaker. But we're putting enough in there so that the pH of the solution is 10.39. Okay, then the question is, what's the hydroxide ion concentration of the solution? So what we need to do is find out what the POH is. Okay, so that's 1,6. 13, right? Oh, no, 3. 3.61. So let's see this. 1 and 9, carry the 1, carry the 1. That's right, 3.61. So the OH concentration would be 10 to the minus 3.61. And we've got 2 decimal places, so I can have 2.5 times 10 to the minus 4. .5 times 10 to the minus 4 right there. All right, that was 40. Let's see, do we want to do 41? Choose the pair of concentrations that cannot be in a given aqueous solution at 25 degrees. Oh, okay. This one's going to take a little legwork. All right, so what do we know about aqueous solutions? We know that Kw, the equilibrium constant for the dissociation of water, is always active, no matter what else is going on. So if we know the concentration of hydrogen ions, we should be able to determine the concentration of hydroxyls. Okay. So 41 relies upon this relationship. Okay. So if A says hydrogen ions, let's just take hydrogen ions right down the line on the left and calculate the OHs and match them up. So if this one is 10 to the minus 13, what's the pH? Well, what's the OH minus? Right? If this is 10 to the minus 13, then the OH minus is equal to 10 to the minus 14 divided by 10 to the minus 13, right? Because these two together equals that. That one times that one equals that one. So this one here is equal to this one divided by that one, right there. So that's equal to 10 to the minus 1. Okay? A, it says it's 1 molar, not 10 to the minus 1 molar. So A is false. That answers the question. Right? If we do the same thing for the rest of them, if we say this one is, let's just do them. If hydrogen ion is 10, what is that? That's 10 to the first power, correct? So the OH is equal to 10 to the minus 14 divided by 10 to the first power, which is 10 to the minus 15. That's true. The other two we can look at. This one we know, 10 to the minus 7, 10 minus 7, that's a neutral solution. We've already talked about that one. 10 to the minus 3 divided into 10 to the minus 14 is 10 to the minus 11. Right? Right? So that one's true. So all of these B, C, and D are true. A is false. That's the answer to this question. I got 42 mark. Click C. What's the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide in enough water to make 3.2? Okay, let's do this one. 42. It's kind of like the very first one we did. Uh, 96.1 grams. Of sodium hydroxide, which is a strong base. So every bit of this is going into solution. And then the volume is equal to 3.2 liters. So we need to convert this to moles. Right? We need to calculate the molar mass of sodium hydroxide. So sodium is 23.00, oxygen is 16, and hydrogen is 1.01. So that's 40.01. There we go. So let's divide that into 96.1. I get 2.402. Now, that's moles of sodium hydroxide. We need to know moles of hydroxide. Well, there's one hydroxide for every mole of sodium hydroxide, so that also is hydroxide. That's not concentration. That's amount. Okay, now we can calculate the molarity. 2.402 divided by 3.2. This is moles per liter. And I get 0.75, two significant figures. Oh, we need to know the pH. Sorry, we're not done yet. So this is molar hydroxide. So what's the easiest way to get to pH? Calculate the pOH and subtract it from 14. So I've already got it in my calculator. I'm just going to take the negative log of that, which is 0. 0.125. And then pH would be 14 minus 0.125, which should be 13 point, let's see, 5, 7, 8, 5, carry the 1, 10, yep, 13.875, or round it off. It should be 2 decimals, 13.88, right there. All right, that's 42. And that's the last one I have marked. Let me see if there are any others in here that would be useful. Back up and look at some we haven't covered. You know, perhaps, let's see, where was that one that I was going to check on? $37. All right. My explanation in the work problems is, in my opinion, incomplete. I just state blanket that NH4 plus is the weakest acid. So that makes NH3 the strongest base. And it may be true, but I don't give any evidence for it. So maybe what I should do is, we've got plenty of time, I should actually look up those values. Let's see. Let's see if they're in my general chemistry book. I don't think they would be in your book. pH. Here we go, acids and bases. Okay. I'm going to write these up here. And this is, we're going back to 37. So for 37, what we need to know is, what's the strength of the acids? Right. The weakest acid makes the strongest base, strongest conjugate base. So let's say HCN, and these are the K values. We talked about the Ks at the beginning, the first lecture. So HCN is 6.2 times 10 to the minus 10. 6.2 times 10 to the minus 10. Then we have HOCl. HOCl, is it here? Yep. 3.5 times 10 to the minus 8. And then we have NH3, so the acid for this one would be NH4 plus. And that was 5.6 times 10 to the minus 10. And the last one is HF. Is 7.2 times 10 to the minus 4. Okay. Now that we've got those numbers out there, I'll refresh your memory on what they actually mean. These are the acid dissociation constants for those acids. So for instance, this one is going to make that plus that. All right. So the Ka for that one would be equal to these, like that, divided by this one. Okay? That's what that means. So, if we compare these, and we're looking for the weakest acid, so we want the smallest value of K. Why? Because the weakest acid will produce the smallest numerator and the largest denominator, which means most of it is over here, and very little of it is over there. That's a weak acid. And we do that. And the way you tell that numerically is first you look at the powers of 10. Right? The most negative number, powers of 10, is the weakest acid. And if you have a tie, like this one and this one, then you go to the coefficient and say, all right, so which one makes the smallest value here? 5.6 is smaller than 6.2, so this one is a weaker acid than that one. Not by much, just a little bit. Notice this one is too big. -4, -8 is too big. -10 is the weakest acid. And this one, being 5.6, makes it the weakest. So the answer is correct. As it was before, it should be C. It's just that the explanation was incomplete. But when you look at the numbers, you actually see which one is the weakest acid. The one with the smallest K is the weakest acid. And the weakest acid produces the strongest conjugate base. Okay. Let's see. I was looking for some that we might have skipped that would be useful. I don't think there are anymore. I think we've covered all our bases. Or if you feel comfortable for the next exam, what we'll do is, let's see, this is Tuesday. So the exam will be on Thursday, and then we'll introduce the last topic, which is redox reactions in electrochemistry. So when we say redox reactions, think batteries. Batteries are a practical application of redox in electrochemistry.